Welcome to a video on solving applications of linear programming using the graphical method with Desmos. In this video, we're going to look at a problem that asks us to find the maximum income. Let's get started. In this video, we'll follow these steps to solve an application of linear programming with the graphical method. We're going to define our variables. Then we'll write the equation of the objective function and identify the goal, whether we want to maximize or minimize. Then we'll write each constraint as an inequality. Once we have the problem set up, we'll then use Desmos to graph the feasible region, identify the corners of the feasible region. Finally, we'll evaluate the objective function at each corner and determine the solution. Let's take a look at our example problem for this video. Kelly runs a restaurant that sells two kinds of desserts. Kelly knows the restaurant must make at least 25 dozen and at most 45 dozen white chocolate blizzards. The restaurant must also make at least 2 dozen and at most 15 dozen mint breezes. Each dozen of the white chocolate blizzards takes 5 ounces of flour, while each dozen of the mint breezes requires 9 ounces of flour. The restaurant only has 315 ounces of flour available. If a dozen white chocolate blizzard generates $2.92 in income, and a dozen of mint breezes generates $2.11 in income, how many dozens of the desserts should Kelly have the restaurant make to maximize income? The first two steps are to define our variables and to write the objective function. To identify the objective function, look for the goal of the problem. In the very last sentence, we see that the goal is to maximize income for this restaurant. Let's let I represent the income in dollars for this restaurant. To identify the rest of your variables, look for what the objective depends on. In this case, I want to look for what does the income depend on. In that same sentence, we see that the income depends on how many dozens of the desserts this restaurant sells. So we know the restaurant makes white chocolate blizzards and mint breezes. Let's let these be our two variables. So let's let X represent the number of dozens of white chocolate blizzards, and let's let Y represent the number of dozens of mint breezes. We've defined our variables. Now we want to write our objective function. To write our objective function, you want to focus on the relationship between all three of these variables. Continuing in that last sentence, we see that white chocolate blizzards generate $2.92 in income and mint breezes generate $2.11. Now we can use all of this information to write our objective function. When I'm solving linear programming problems, I usually like to organize my information in a table. This is not required, but it just helps you organize all of the information and write the equations or the inequality. In the first row of my table, I'm going to write our objective, and that is to maximize our income. Next, in the two columns, I'll write my variable. So white chocolate blizzards and mint breezes are the two variables in this problem. Just below income, let's also take a row to represent the quantity or the number of dozen. We used X to represent the number of dozen white chocolate blizzards this restaurant makes, and Y to represent the number of dozen of mint breezes. We also learned that this restaurant earns $2.92 in income per dozen for white chocolate blizzards and $2.11 per dozen for mint breezes. Putting these ideas together, the total income would be $2.92 times X, or the number of dozen white chocolate blizzards, plus $2.11 times Y, or the number of dozens of mint breezes. So our objective function would be the equation I equals 292X plus 211Y. Now that we've got our objective function, let's look at how we write the constraints for this problem. The constraints are requirements or limiting factors. If you have trouble identifying the constraints, look for the key phrases that suggest an inequality. Constraints are usually written as an inequality in linear programming problems. So look for phrases like at most, at least, no more than, etc. Rereading the problem, we see our first requirement and limiting factor is in the second and third sentence. It says Kelly knows the restaurant must make at least 25 dozen and at most 45 dozen white chocolate blizzards. Those two phrases, at least and at most, tip us off that one of the requirements and a limiting factor are the number of dozens of white chocolate blizzards this restaurant needs to make each day. Continuing on, it says the restaurant must also make at least 2 dozen and at most 15 dozen mint breezes. So another constraint is how many dozens of mint breezes this restaurant needs to make each day. This information relates to the third row in our table. For the white chocolate blizzards, this restaurant must make at least 25 and at most 45 dozen. That is a constraint that only revolves around the white chocolate blizzard. So it only relates to X. X, which is the number of dozens of white chocolate blizzards, must be between 25 and 45. As an inequality, we would write that as 25 is less than or equal to X is less than or equal to 45. The problem also stated that for mint breezes, this restaurant must make at least 2 and at most 15 dozen mint breezes. That constraint only focuses on the number of dozens of mint breezes, which we represented using the letter Y. So in this case, Y must be between 2 and 15. As an inequality, we would write that as 2 is less than or equal to Y is less than or equal to 15. There was one more constraint in this problem. Toward the middle of the paragraph, we see that this restaurant only has 315 ounces of flour available. So one of the constraints is how much flour is available. Even if this restaurant wanted to make 300 dozen desserts, it would not be possible since there is a limit to how much flour they have. Whenever you want a constraint, you usually need to see how it relates to the variables. So we need to see, how does flour relate to the number of dozens of white chocolate blizzards and mint breezes? Backing up just a little bit, in the previous sentence it says each dozen of white chocolate blizzards takes 5 ounces of flour, and while each dozen of mint breezes requires 9 ounces of flour. So now we know flour is a constraint, and we also know how flour relates to our variables. Let's use this information to write our next inequality. In the last row of my table, I'm going to write the constraint revolving around flour. We know white chocolate blizzards require 5 ounces per dozen, while mint breezes require 2 ounces per dozen. So total, that's 5x plus 2y, and we know the restaurant only has 315 ounces of flour available. As an inequality, this says that 5x plus 2y is less than or equal to 315. So the total flour that we use to make the white blizzards and mint breezes cannot be more than 315 ounces the restaurant has on hand. Let's summarize where we're at. We've now set up our linear programming problem. We need to maximize the income, which is the function I equals 292x plus 211y, subject to the following constraints. 25 is less than or equal to x, which is also less than or equal to 45. 2 is less than or equal to y, which is also less than or equal to 15. And 5x plus 9y is less than or equal to 315. To finish solving this problem, we need to graph the feasible region, identify the corners of the feasible region, and then evaluate the function at each corner to determine the solution. Let's go over to Desmos and use the equation and the constraints to solve this problem. To get started, go to the website desmos.com, click on the button that says Graphing Calculator in the center of the screen, or from the Math Tools menu, choose Graphing Calculator. When the Graphing Calculator opens, go over to the left-hand side and enter the objective function and each of the constraints into the cells on the left-hand side. As you can see, I've already entered these here. Let me go ahead and turn these constraints on so we can see the graphing area. To locate the feasible region, you may need to zoom out on the graph. You can use the mouse to zoom out or the plus and minus buttons on the upper right-hand side. Let's zoom out so we can see the feasible region. The feasible region is going to be where all of the inequalities are satisfied. That means that we're looking for the area where all of the shaded regions overlap. It looks like it's this little corner right here. Let's start to zoom in a bit more. So I can see that the three areas, the red, the green, and the purple, all seem to overlap in this one polygon here. Let's adjust our graph settings so we're only looking at the area where they overlap. On the right-hand side, click on the wrench to set the graph settings. Under the x-axis, let's change the x-axis to view from 20 to 50. And let's change the y-axis view to be from -2 to 20. I'm going to go ahead and lock the viewport so I can focus on this area of the graph. What we want to do now is to identify the corners of our feasible region. As I identify the corners, I'm going to add them to a table. To add a table, click in a cell and then go up to the top left-hand side where it says Add Item and choose Table. It doesn't matter where you start at, but it's always a good idea to enter the corners into this table in either a clockwise or counterclockwise fashion. So I usually just pick a starting point and then I'll go around. So our first one is 25.2. Next we have 25.15, then 36.15, then 45.10, and 45.2. I've now added all of my corners to the table. This next step is optional, but I like to draw a polygon around the feasible region so I can concentrate on only that area. To draw a polygon using your corners, type the command polygon followed by parentheses with x1, y1 into a cell on the left-hand side. I'm also going to change the color to black just so we can see the feasible region. Now that I'm looking at the feasible region, I'm going to turn off the shaded area to the constraints. Now we've drawn our feasible region and we've identified corners of the feasible region. The next step is to evaluate the objective function at each of the 5 corners. Desmos makes this really easy for us. Go back to your table where you entered the corners. Click on the third column at the top next to where it says x1, y1. Type in the right-hand side of the objective function. Replace x and y with x1 and y1. So I'm going to type in 2.92 x1 plus 2.11 y1. So Desmos has taken all 5 of the points in our table, which were the 5 corners, and it has evaluated our objective function at those 5 corners. Now all we need to do is locate the maximum value. It looks like our maximum value of these 5 numbers on the right of our column is 152.5. So our maximum is going to occur when x is 45, y is 10, and our maximum value would be 152.5. Let's go back and summarize our answers. We found our solution was at 45.10. This means that to maximize income, the restaurant should make 45 dozen white chocolate blizzards and 10 dozen mint breezes. If they do this, they'll have a maximum income of $152.50. That's it for this video. Thanks for watching.